Today on the bench we've got something pretty special. This is a pair of Stromberg Carlson AP-437 tube monoblocks. These amplifiers were made by Stromberg Carlson in the late 50s and perhaps until 1960 or 1961. There's really not much information on them online. And what makes them really special is a few months ago they were brand new. They were in the boxes. Someone found them in a storage unit, I guess was the story. They had all the original tubes with them, also in their original boxes. And here's a view of the box itself. You can see the label on it there. Both of them are with their original boxes. And the story with these is that a few months ago I was talking to the owner of these amplifiers about restoring them for him. He had posted a thread asking for help bringing them up on a variac, and I suggested, due to the fact that they've been sitting for so long, that you shouldn't just bring them up on a variac. They need to be gone over, and there's many parts inside that need to be replaced. He ended up finding someone locally that seemed to be okay with not replacing things like the electrolytic capacitors, and he was also closer, so I don't blame him for going there for that reason. But unfortunately, kind of what I said was probably going to happen ended up happening, and he got some hours on them, and the story goes that he was playing them, and he saw some arcing in one of the rectifier tubes, and then the amplifiers, which use a circuit breaker instead of a fuse, the circuit breaker popped. So he went and put a different rectifier tube in, turned it back on, and he had said the same thing happened where he saw some sparks in the rectifier and the circuit breaker popped again. So we're going to take a look at these and see what the other tech did. I'll give you a hint, it's not much. And we're going to bring them back into spec and make them reliable so he can enjoy them. Okay, let's take a look at some documentation on this amp. So the first thing I'm showing on the screen is the 1958 Stromberg Carlson catalog. This is the earliest catalog I can find. And we see the amp pictured here on this page with a brief description. And if we continue to scroll down, we see some specs here. So there's AP-437, 40 watts rated power, 80 watts instantaneous peak. Frequency response 20 hertz to 20 kilohertz plus or minus 0.1 dB at 40 watts. And they also list down a little bit here, so alternate test conditions, 10 hertz to 60 kilohertz at plus or minus 1 dB at 40 watts, or 10 hertz to 100 kilohertz plus or minus 1 dB at 10 watts. Okay, they also list the harmonic distortion as 0.5%, 20 hertz to 20 kilohertz at 40 watts. And they mentioned below again 0.1% at 40 watts if you limit it from 100 hertz to 10 kilohertz. Our intermodulation distortion is listed as 0.4% at 40 watts. And they have another caveat there, and they specify 60 hertz and 7 kilohertz was the mix of frequencies they used at a 4:1 ratio, which is the industry standard for the most part. Hum and noise 90 dB down. They don't say if that's A-weighted or not. And input sensitivity, one input variable from 0.7 to 10 volts. Then if we scroll down a little bit, there's some additional specs here showing, output impedance is 4, 8, or 16 ohms. And it shows the tube complement. It mentions a selenium rectifier for the bias voltage and the dimensions. And one thing you'll notice is in this catalog there are no consoles featured that use this power amp or a pair of these power amps. But if you jump to the 1961 catalog here, you see the amp again mentioned, and it lists these two monstrous consoles that would have had a pair of them in each, the SP991 and the SP993. I read somewhere online that the list price on these was somewhere around $4,800 in 1961. Not sure if that's true or not, but that would have been equivalent to $51,000 in today's money, which, I mean, given how large they are and their complement of components listed here, seems reasonable. These had a manual turntable. They had a 4-speed changer. They had a stereo tape deck. They had the Stromberg Carlson SR445 AM/FM stereo tuner, a pair of these amps, and then the ASR434 preamp. And then they had a pair of these RS424 speakers built in. So that'd be pretty cool to own one of those. Here's a close-up of the amplifiers. See, the cover is a snap fit onto these studs here, which is really nice. So it's got a 7025. That's what it came with, a 7025, which was, I guess, a lower noise version of a 12AX7. You can also run 12AX7 in it. I'm not sure what brand the 7025 is. There's no labels on it other than the number 7025. I'm not a tube expert, so I can't tell just by looking at the plate structure and the font on the numbers to be able to tell. But the 12BH7 is a Stromberg Carlson branded tube. I think it's made by General Electric. And currently we have some modern Electro-Harmonix KT88s and a JJ5AR4, but we have the original tongue sole tubes in the boxes over there, and I believe it's a Mullard 5AR4. So we can see we've got a hum control, AC balance, bias. I like these little plastic caps they have on the controls. That's pretty nice detail. We have a gain control, RCA input, power light, speaker selector, which is kind of unique for a monoblock amp like this. You don't see that too often. Our terminal strip for the outputs, and power switch. Here's the other one with the cover on. These aren't sequential serial number, but they're not far off from each other. Apparently there was a few variations of these, but these ones do have the same exact circuit. Here's a view of the bottom, and there's just 4 screws on the side you take off. This cover is kind of tricky to get out. You want to use some plastic pry tools to get at the edges and kind of rock it up and out. So I'll go ahead and take that off and we'll be right back. Now here's a cool detail you don't see every day. They actually pasted a copy of the schematic on the bottom cover of the amplifier. That's really nice. Okay, and let's take a look at the inside. So from my understanding, this is the one that had the issue. And you can see right away that the last technician that was in here, all he did was replace the 2 coupling caps with orange drops. Everything else is original. He left the original filter can. That's the one I was really concerned about when I originally talked to the owner. A lot of people say you can reform these things, but on something this rare, it's not worth even attempting. The longer that they're in storage, especially unused, the worse your chances are at them being usable. And I mean, this thing is 65 years old. I don't care if you can reform it or not, don't use it. We can see that the original bias components were left in place, the electrolytic capacitor and the selenium rectifier. We're going to replace that with silicon and adjust the resistor for the correct voltage range. And you can see these other 2 paper caps were left in, and all of the carbon comps were left in, carbon comp resistors. I'm willing to bet that the majority of those drifted high. I'm not actually sure what happened. I'm not going to try to reproduce the issue that he had. I already know that there's a lot of components in this thing that shouldn't be in here, so we're going to replace them and then test it out and go from there. And you can see there's a circuit breaker here instead of a fuse, which is kind of nice. Okay, so the plan is we're going to replace the can capacitor with an authentic cap 40-40-20-20. The original is 30-30-20-20, but this is the closest we can get while maintaining kind of the original look. The other thing we're going to do, we're going to rebuild the bias supply. I've got some new caps here. These are 68 microfarad, 160 volts. We'll replace that with a silicon diode. We'll replace these other 2 paper caps. The input coupling cap, I've got a 0.22 250 volt. We've got a 0.47 630 volts to replace this guy here. And we will replace the resistors as needed. And we'll make sure to use low noise resistors in the spots that matter. You know, I've actually had a stash of these 15K Dale RN65Ds, so I'll use that in the feedback loop. That's a 15K there. And this is actually kind of interesting too. If you look at the schematic, the feedback has its own winding on the transformer instead of just tapping off of the 16 ohm tap like most of them do. And this is not ultra linear. It has its own separate screen supply here. We'll also install an inrush current limiter. So we'll use either a CL80 or a CL190. He mentioned that his line voltage at his house consistently measures at 117 volts. And if you watched my last video on the Dynaco Mark III, you saw that a CL80 drops about 2.5 volts. So that'll get you from 120 to like 117.5. So if he's already at 117, and this was designed to run on 117, we might not want to drop so much voltage. So we can use a CL190. I have to do some measurements and get the exact current draw on this to see if this is within spec. This is rated to 2.4 amps, whereas the CL80 is rated to 3. But we saw the Dynaco Mark III, which basically has the similar tube complement, draws less than 2 fully loaded. So I have a feeling we can use the CL190, but we'll figure that out when we get to it. And here's how you take this front cover off. You want to use a plastic pry tool. This is a body panel kit from Harbor Freight. And you kind of start on the bottom, work it in there, pop it off, do the other side. You want to kind of lift up on the front at the same time so it doesn't scratch the paint on the front lower edge. And then this just pops off. So one other thing that I didn't like about this was the proximity of the capacitor can to the extremely hot tubes, the KT88 and the GZ34. They get really hot. So what I'm going to do is I made up these little panels out of galvanized steel flashing, and we're going to use some little neodymium magnets on the bottom there so it can just be set in. I have to trim it a little, it's too big right now. But that'll shield the capacitor from the radiation, the heat radiated off these tubes. And if he doesn't like it, he can just pull it off because it's just going to be held on with magnets. So for regular use, keep that on. And if you're ever showing these off, just pull it right off. There'll be no marks below, no holes drilled, nothing. So I think that's a pretty good solution. Just started working on the amp. Got the new capacitor partly installed. And I've been starting to check the resistors, and they're all drifted pretty high. Like if we look at one of these bias resistors here, which is 100K, I believe. It's reading 116.5, and the other one 123. So I decided to record the values of all the parts that I removed from the amp as I pulled it out, since I wasn't really finding a good root cause as to what would have tripped the breaker on him. I had originally suspected that the filter can shorted. That's the most likely cause, in my opinion, of this issue happening, based on the fact that the thing's 65 years old and hasn't been energized since it was built in the factory. It's pretty well known that the longer they sit on the shelf, the worse they get. Like, you're better off having energized them sporadically over the years. So I measured the can capacitor first, and the first one was actually pretty close to spec. So this has two 20 microfarad sections and two 30 microfarad sections. The 20s are rated at 400 volts and the 30s at 500. And as you can see here, we got some numbers that were definitely within the tolerance. And on the second amp, the numbers were definitely in tolerance too. Because remember, these old caps, the allowance on the positive side was pretty high, sometimes like 150%. And I also tested the ESR, and the ESR was low on both, below 3 ohms on all the sections. And then I did a leakage test. I don't have the procedure that they used when they built these exact caps back in the day for leakage, so it's possible that they allow more than is allowed nowadays, given how old they are. But I just went with the standard formula of 0.03 times capacitance times voltage. And I see that, so in this column here, this is what I calculated as the allowable microamps of leakage, and the first capacitor is not above that. The one section is just barely above that, but we'll just consider that to be within the margin of error. And the capacitor from the other amp, it failed on 2 of the sections, but again, it wasn't a dead short or anything like that. And I do notice that these get significantly worse with heat. I played around with a heat gun and watched the leakage creep up well over 1 milliamp after just a few minutes, and that was nowhere near as hot as it's getting in these amps next to the tubes. So I guess it's still possible it could be related, but not a smoking gun. And I also measured the carbon comp resistors when I took them out, and out of both amps, 6 out of the 16 were out of spec, and some other ones were like right at 9-10%. So we ended up replacing all the resistors in here with all metal films. So I was working on this amp. This is the second one. We'll call it amp B. And I have it mostly rebuilt. It's actually pretty much complete at this point. And I turned it on the dim bulb tester in the Variac to make sure everything was good. Everything was great. I adjusted the bias and let it run for a few minutes on 300 watt dim bulb, which wasn't lit up very much because it wasn't pulling near 300 watts. And everything looked good, so I tested on the audio analyzer and got a nice clean sine wave, so I let it run for a few more minutes, and I took it off the dim bulb tester, ran great for a few minutes, and then suddenly the breaker popped on it. And I noticed, I was looking at, I had multimeter hooked up to a few different points here, looking at the plate voltage and the bias voltage, and I noticed right before the breaker popped, all of a sudden the bias voltage started jumping around, and I thought that was really strange. So I, obviously, the breaker popped, I turned the power off, and then I pulled the rectifier tube out, took a look around. I didn't see any components that had failed or shorted or resistors that blew up. Everything looked great. And I was getting really confused because what I was seeing here on the schematic is you've got the rectifier for the bias circuit, and then you've got your first resistor, which was originally a 4700, which we changed to 9K to get the adjustment range the same without the selenium rectifier and switched to silicon. And what I was seeing was like less than negative 1 volt here, where it's supposed to be negative 45. And I couldn't figure out for the life of me. It was really confusing. And ultimately, I ended up disconnecting everything from the bias pot here. And what I saw is between the center terminal, the wiper, and I think it was this terminal here, between either of those two terminals, with nothing, mind you, nothing connected to this pot at all at this point, I saw like 90 ohms between the outside case of the pot and the chassis or the ground of the amp. And one thing that I'll say is that when I did the work on this, I'm really careful when I'm cutting leads off and removing old parts and soldering that I don't let any loose leads go flying around, because they can kind of get into the pot there if you're not careful, or get underneath it and short it. And I accounted for everything when I worked on this. So I ended up taking the pot out, and as I was taking it out, I was very careful, and I was looking to see if there was anything that might have got stuck under there and caused it to short or anything like that, and there was nothing. So I took the pot apart, and I noticed some gray fuzzy stuff on the back of the wiper here, which is up against the bottom of the case when it's put together. And I didn't realize what it was at first until I posted a picture on a group that I'm in, and some friends said, "Oh, that's tin whiskers." Almost looked like velvety. And, you know, as soon as I took the case off, obviously there was no more case there. There was nothing wrong with the pot inside. The carbon track is practically brand new because these were new, and there was no debris or grime, anything. So I ended up scrubbing off that gray, velvety looking stuff from the back of the wiper, put it back together, and there is no continuity between the case and the ground of the amp now. So I think the tin whiskers shorted the back of the pot. So what we're going to do is I'm going to go to the other amp, the first one I rebuilt, amp A, and we're going to remove that bias pot and see what that one looks like. Because the owner of these told me that amp A is the one that actually tripped the breaker when he had it. And amp A, I didn't necessarily find anything wrong with it. The capacitor I didn't like, the filter can. It had higher than acceptable leakage in 2 of the sections, but there were no dead shorts or anything. So there was no smoking gun. So I'm really curious to see what we find in this other pot. Okay, so I've got the pot removed from the amplifier, and we're going to go ahead and pry it open. Let me get this zoom out a little bit here. So we're just going to pry up on these 4 tabs around the side, and we should be able to get in there. Okay, now I'll use this pair of pliers here to try to bend them up nice as I can. And I did measure this one. There was no continuity between the chassis ground or the wiper either end of this, so I'm not expecting to see anything, but we're going to check it just to make sure. So we don't want anything happen to him when he gets this back, happening to these amps. Alright. Okay, and it's got the same thing going on. There it is. Look at that. That's crazy. How's the zoom there? So that's not supposed to look like that. Isn't that wild? This looks like our tin whiskers. So on the other one, all I had to do was scrub it with isopropyl alcohol, and they scrubbed off. I'm going to take some closer pictures of this first before I clean it, though, because that to me is just insane. Okay, so I've got one of the pots with the tin whisker problem under my cheap USB microscope here. Let's see if we can get a better look at it up close. You'll have to bear with the shakiness here. I'm kind of holding this by hand and trying to focus with the other hand. So there you can see the whiskers coming down, and looks like the one on the left might actually be making contact with the brass colored part there. I posted this in a couple Facebook groups, and there's a bunch of people posted, people that worked in the aerospace industry for Boeing and Hughes and worked on satellites and things that had to work on tin whisker mitigation programs, and they said they've never seen anything this bad. This is definitely one of the worst cases of it that I've seen from my research on the internet in the last couple of days. Isn't that cool though? A couple long ones too. So alright, we're gonna get this cleaned up and get this other amp back together. Okay, so now that I've got some pictures so people actually believe me, I'm going to go ahead and clean it off. I noticed it just kind of wipes off with isopropyl alcohol and a Q-tip here. So again, there's our tin whiskers. I'm not sure if this is, yeah, it is actually removing them. It's not just flattening them out. So we'll do this a bunch. There they are on the Q-tip there. Get down in there. I'm going to have to do this a couple times. Get that little bit on the back side there. And you might be asking why I don't just replace these, and well, I'm going to look into it honestly, because I'm not too happy about this. You know, they're sometimes hard to find in the old form factors. So I spent quite a bit of time doing some parametric searches at both DigiKey and Mouser looking for some replacement pots. The only ones I were able to locate that are close fit are the RV4 style military spec pots, and they're very expensive, as you can see on the screen, $150. And they were the only option with the round slotted short shaft like the originals. I want to maintain the original look on this amp, and the other problem is that the plastic cap that I showed earlier likely wouldn't fit on these RV4 pots because they have their own special tapered fit and a locking nut, but they're the closest match. And the next best option was some Bourne's pots that were close to $20 each, and they had a long shaft, so I would have had to grind that off and all that if I wanted any semblance of the originals, and that's not practical. What I read is that if you cover them with an acrylic coating, it should prevent them from coming back. Alright, I've got it cleaned up fairly well. I'm probably going to go through this with the tweezers under a magnifying glass to make sure there's no cotton debris left, but you don't see any of the fuzzy stuff anymore. And then what I'm going to do is, I've got this MG Chemicals 4190 acrylic conformal coating, and I'm just going to dab it on there with a Q-tip. I don't want to use a paintbrush. I don't have anything small enough, but that should help. Okay, so here it is with, let me try this. Here it is all cleaned up. There's like no evidence of them at all anymore. I just picked all the rest of the cotton swab out of there with some tweezers, and then I flushed it out with the CRC quick dry. So we're going to go ahead and paint that acrylic on there now. I guess I'll try to do it on camera, not that there's much to see, but I'm just going to dab this. Don't want to make it too thick. Drip it on a little thick there so it kind of runs. There we go. It ran down to the bottom edge. That's what I wanted to see. Alright. Well, it's not the prettiest thing, but I'm pretty sure it's all encapsulated now. So there we go. So I'll hang this upside down to dry so it doesn't run onto the wiper or anything. Not that it will, but... And hopefully that gives this thing another 65 years or more. Okay, well I've got that one cleaned up and I've got the acrylic conformal coating applied. In the meantime, I've been reading some more on the internet. I did find NASA mentioned this exact problem with the pots, and Westinghouse Nuclear apparently had a service bulletin for pots that had this problem in some power supplies, and they actually suggested the same thing: scrub it off with a soft bristle brush and apply a conformal coating over it. So it makes me feel good about the fix. I assume the other, how many pots are left? There's 2 AC balance pots and one more gain pot. I'm assuming they're going to have the same problem, so I won't videotape them, but I'll report back with what I find. Okay, well I know I said I wasn't going to show anymore, but this is the last one in this amp. This is the 50K pot, which is used for the AC balance, and this one is also bad. There we go. Tin whiskers all over it. Okay, so here's a look at the bottom of the amps after the work's been completed. We did leave the orange drop coupling caps in that the last technician installed. The other thing is, I'll say that these followed the schematic actually pretty much spot on. The only thing that wasn't on the schematic was this 100 picofarad cap here across R3, which is a 100K resistor. So when I replaced R3, I put a new silver mica 100 picofarad cap in there. And we added the CL190 inrush current limiter here. I'll share some pictures on the screen, but basically the CL190 is rated to 2.4 amps continuous. I measured these amps fully loaded at 2 amps. So that should be a perfect fit, and the resistance of it is a bit lower than a CL80. So like I mentioned earlier in the video, his line voltage at his house, he said, was around 117, so we didn't really want to drop much voltage, so that's really a better fit than the CL80. I used the HP6813A AC power source to perform some inrush current testing. I set this up the same way that I did in the last video with the Dynaco Mark IIIs. HP in the manual suggests a 70-degree turn-on phase angle for the worst possible scenario. So you can see here in the first test with no inrush current limiter, there's a pretty massive peak amperage on the first cycle, and there's the current waveform there. It's not very pretty looking. And if you look at the results with the CL190 installed, that peak no longer exists, and the waveform basically follows the AC power waveform. So that's definitely going to give this thing a softer start and help prolong the life of the transformer as long as possible. Other than that, we replaced all the resistors with metal films. Too many of the carbon comps had drifted high, and I wasn't going to leave just a few in there, so they're all new. And in the bias circuit, we replaced the selenium rectifier with the silicon diode. Just used a 1N4007 or a UF4007. And replaced the 4.7K resistor here, R16, with 9K of resistance. And I found that matched the original range perfectly. I put two 18K resistors in parallel there since 9K is an odd value. I could have used 9.09, but I didn't have any of those on hand. So yeah, I'm really happy with how these turned out. I've actually already tested them out and put some time on them with the electro-harmonics tubes in them, but I've gone ahead and put the original Stromberg Carlson tubes in that we just tested, and we're going to go ahead and get them biased up and also tweak the hum control and the balance control. So I measured all the tubes on the TV7 tube tester, but I also wanted to try to match them for plate current with the Tektronix 570. Now I'm still learning this. I've only had it for a few months, but I think I've got the right idea here. I also looked at some Amplitrex tube data sheets for 6550s that I saw, and the way that they're doing it seems to line up with what I'm doing, which is really looking at the data sheet for the 6550. So we're in the 6550 section here, and we're looking at the typical operation and characteristics section. So they give you an example with a 250 plate voltage, 250 screen voltage, negative 14 volts of bias, and they're saying we're at around 140 milliamps and 11,000 transconductance. So I've got the curve tracer set up for that, and I've already got all the settings dialed in right now, so I'll go ahead and flip it over to grid A, and you can see each horizontal line is sort of zero bias is the top line, and then there's -2, -4, -6, -8, -10, -12, -14. So I'm going to change the vertical scale from 50 to 20 so we can get a better measurement of the -14. And we're at 0 volts here, 500 volts here. So this is the 250 right in the middle, and that's where we want to take our measurement. So we can see that the 250 volt mark is at, there's our 100 milliamps, it's 20 per vertical division, so we're at 120 milliamps for that reading. And as far as the transconductance goes, the way I understand that is it's the difference in plate current here, which is 22 milliamps, divided by the difference in grid voltage, and there's 2 volts here since each step is 2 volts, so that's 11,000 transconductance, which lines up with what the manual says. Alright, let's talk about how we are going to adjust the bias, balance, and hum. So if you look at the instructions for the amp, they have a pretty basic procedure here on adjusting the bias and the balance. They don't tell you how to adjust the hum, but we'll cover how I'm going to do that. So first you need some equipment. You need the audio oscillator, the amp obviously, an AC voltmeter and a distortion analyzer, and of course an 8 ohm dummy load. So their instructions go, set the gain control to 0.7, which is fully clockwise, and then they want you to adjust the output signal of the oscillator until you see 18 volts AC with a 20 hertz signal across your 8 ohm load, and I determined that already to be around 587 millivolts. And then they basically tell you adjust the balance control for minimum distortion, should be less than 1%, and adjust the bias control for minimum distortion. Now, they don't specify what idle current you're looking for, and there's no provisions built into this amp like bias test points or anything where you can easily measure it. There's obviously ways to measure it, which we'll cover here in a second, but all they tell you is that with an average set of tubes, you're looking for about negative 38 and negative 40 volts of DC bias. So the way that we're going to check the bias is, well, I'll turn it on and I'll rough it in. I'll set it to negative 40. But before that, what I did was I measured each half of the primary of the output transformer, so between the red and brown and red and blue, and I actually labeled them here. I put a little sticker on the amp. So we've got 47.4 ohms between the brown and red, which is this tube here, and 42.6 ohms between the blue and red, which is this tube here. So I'll go over to the computer here and show you some calculations. So the first thing we're going to do is take a look at a tube bias calculator. I've got the 6550 with 42 watts of dissipation selected and 475 plate voltage. And what that gives us for our Class AB fixed bias is 70% max safe dissipation is 61.9 milliamps, so we won't want to exceed that. And then I'll go to Ohm's Law calculator over here, and we'll punch in the current that we're looking for, which is 61.9 milliamps. Then we'll punch in that resistance that I measured across the primaries of the transformer. So the first half of that was 47.4. So on that half, we're looking for 2.93 volts dropped. And on the second half was 42.6. So that'll be 2.63 volts. So basically, we want to monitor the voltage on both of those as we set the bias, and we don't want to exceed either one of them. So I've got the amp warming up, and I tweaked the bias to around negative 40, negative 41. And we'll go ahead and dial that in a bit more. You can see that the voltage drop across each half of the transformer, that's the top 2 meters, around 2.07 to 2.11, which is around 49 milliamps. So once this warms up in a few minutes, we'll go ahead and bump that up and see where that lands us at as far as negative bias voltage. And if we're in between, if we're at around 60, 61, 62 milliamps, and we're around negative 38, then I think it's pretty safe to say that that's what they were shooting for with this design. And the way that this is set up is that on the top meter we don't want to exceed 2.93. And on the middle one, we don't want to exceed 2.63 because that represents 61.9 milliamps of plate current. And I'm going to go ahead and bring that bias up a bit. Or should I say down? 2.25. Alright, so the bottom one is the 2.63, so it looks like the bottom one's going to hit that number first. So we'll stop there at 2.62. So that would be 61 milliamps. Then the top one's actually biased a little bit below that since it wasn't a perfect matched pair of tubes. And this doesn't have individual bias adjustments. So let's see what that, so 2.64 volts across 47.4 ohms. So that one is 55.69 milliamps. Let's see what the distortion looks like. So I adjusted the bias first, and I'll do the balance next. I want to take a look and see what this looks like at its 40 watt rated output here at 1 kilohertz, just to give me an idea. So there's our 100 millivolts, 1.4 watts, 0.01. Let's see, go up to 400 millivolts. So we're at 22 watts at 0.09, 450, 27 watts at 0.12, 550, I'll do 555. Okay, so we're at 41 watts. Let me back that down a little to 550. So 550 millivolts is giving us about 41 watts at 0.3% distortion, which I'm pretty happy about. And I haven't adjusted the AC balance yet. Well, technically I have. I was playing around with this a bit off camera. So let's double check the AC balance setting. So they want us at 20 hertz for that. And frequency 20 hertz. I'm going to change the unit to volts millivolts so we can get that 18 volts that they wanted. And I'll go ahead and turn this on. Adjust the oscilloscope display. So we're at 0.6%, which is below the 1.0% that they specified. So that's good. So I'm going to adjust the balance a little. I have a feeling it's already probably spot on. So the way I'm going to do it is I'm going to look for that residual distortion waveform, the smaller one, to shrink. And it's actually already pretty much down. I just moved it back and forth a little. Another way that I've read that you can do this is by looking at the second harmonic. So if I go to the THD mode, it's going to read really slow at this low frequency, which is why I like that residual distortion waveform. So our second harmonic is already really low. You can actually see it's, if I select just the second harmonic, it's 0.052%. So the visual method of looking at the residual is really the best way. That's why I like this analyzer so much. Okay, so less than 0.5% THD. Okay, so to adjust the hum, I hooked it up to the HP-3562A. I've got it displaying from 0 to 400 hertz, and I've got the marker on 60 hertz. So with the hum pot, we want to reduce the 60 hertz as low as we can by turning it. And currently the 60 hertz is at negative 59 dB pretty much. So I'm going to go over there and turn the hum pot with a screwdriver and watch that fall in real time and try to get it on the lowest number. I've seen it drop. Let me go the other way. So it looks like right around here is going to be our lowest. I'm a few feet away, so I can't read it on the screen. Okay. Alright, so where are we at? We are at negative 68.5. That looks good to me. So I ran into an issue while adjusting the hum on the second amp. I followed the same process I showed a moment ago where I adjusted it for the lowest 60 hertz component. What I didn't realize is that ended up in the pot being too far to one end. And this is a wire wound pot, but it's actually made out of some type of like compressed paper. and it started burning up after a few minutes, and you could smell like the paper burning. So I took the bottom cover off, and I saw that the pot had just been adjusted too close to one end. So I did some more research on how this adjustment works. Keep in mind the manual didn't have any information on how to adjust it, and in all of the other manuals that I've read, they basically just say adjust it while listening for the lowest 60 hertz out of your speakers. So I did some more reading on it, and I found that you really want to adjust it so that you have half of your 6.3 volts on each end of the pot. So if you connect your meter between one end and the center tap, you should have about 3.15 volts, and the same thing for the other half. So I put a new pot in it, and then I adjusted it for that so it was balanced, and then I played around with the analyzer a little bit, because apparently it seems pretty well known that having that perfectly balanced doesn't always equal the lowest amount of audible hum. So then I adjusted it on the analyzer again, but I was keeping it, as close to the center as possible, and it actually worked out pretty well. So I've got the other amp hum set correctly, and it had about the same result as the first one. Now, interestingly, the first one, I took the bottom cover off after I noticed this just to see where it was at, and it was pretty much in the center. So anyways, that's just something to keep in mind there. Alright, so I'd say we're done adjusting this first amp for now. And what I came to at the end of this was our bias was negative 38 volts measured here at the junction of R11 and R12. So that's within their specification of negative 38 to negative 40. And calculating the voltage drop, so the brown half was 2.64 volts and the blue half was 2.62, so that one tube is at 61.5 milliamps, the other one's at 56. Like I said, they weren't a perfectly matched pair, but that's pretty darn good, and the distortion numbers were looking great. So I'm going to adjust the other amp off camera. So I'm working on the other amp right now. This one's labeled A, and this one is the one that I use the pair of new old stock 6550s. The last amp we just showed, that was using the 6550s that were in the third one of these that he had. It had some use on it. And out of the two pairs I came up with, this was the closest matched pair. And when I measured them on the curve tracer, 250 volts, negative 14 bias, like the data sheet showed, they came out at 102 and 104. And you can see here on the meters, this is the top one. We were looking for 2.95, and the bottom one we were looking at 2.61. So that's much closer than the last amp, which was 2.62 and 2.64. So this is definitely a closer matched pair. So we're at negative 36.5 volts of bias, so we're in line there. I'm going to go ahead and get this adjusted the rest of the way. So on the second amp, amp A, I was able to get the balance control adjusted to the pretty much identical harmonic distortion profile as the first amp. So that's looking good. Okay, so I've got the amps hooked up to the analyzer. We'll do a few tests here. So this first test is going to be THD+N, and I've got it set up so that it's creating 40 watts or so of power, and I'm testing at 1 kilohertz right now. It's off. Those are the results from when I tested it a moment ago, so I'll turn the generator back on here and run the test, control F5. So we can see, so channel 1 is the amp to the left, which is amp A. Channel 2 is the amp on the right, which is amp B. So amp A is at 0.46% at 40.23 watts with a 555 millivolt signal going to the amps, and amp B is 0.33% at 41 watts. So there's a slight difference in power, but probably attribute that to a slight difference in the gain pot or a slight difference in the 7025 tube on the input side of it. But I'm really happy with those numbers. The spec was 0.5% from 20 hertz to 20 kilohertz when it measured at 40 watts. And we don't really know all of their measurement conditions. You know, they could have had A weighting on, for example. So if I go here and I turn on A weighting, let's see if I can find that. We might see better results even. Let's see. I'm honestly not sure where that is here. Here we go. Actually, it's under filter. I'm still learning this analyzer. So there's our A weighting filter. A weighting actually made it a little bit worse in this case. So there it is, A weighted. It jumped up to 0.53 and 0.38. I'll turn that back off. Let's do a couple more THD+N measurements at different frequencies, still at 40 watts. We'll change the frequency to 100 hertz. 5. Give it a moment to update. So at 100 hertz, it's about the same, 0.48 and 0.32. Try 500 hertz, 0.47 and 0.33. Try 5 kilohertz. We already did 1 kilohertz. It's 5 kilohertz, 0.54 and 0.40. Now if I go to 10 kilohertz, it's only going to get the first harmonic because the analyzer bandwidth is only 22 kilohertz, but we'll go to 10 kilohertz here. So 10 kilohertz, it's saying 0.22 and 0.16, but I think that's mostly because of the limited bandwidth of the analyzer. Like if I say 15 kilohertz, it's probably going to be even lower. Yeah, 0.009. And that's a difference with this analyzer and its 22 kilohertz bandwidth versus the VP7725D. And I'm still trying to figure out what the standard is for measuring THD+N, because I believe a lot of the other analyzers on the market have filters that are turned on by default, or they have a limited measurement bandwidth. It's mentioned in the Audio Precision Audio Measurements Handbook that there's usually a high-pass filter and a low-pass filter. I've heard a high-pass of 200 or 400 hertz that's supposed to filter out some of the noise from the power supply, the 60 hertz and the 120 hertz. And I've also heard of a 22 or 30 kilohertz low-pass filter on the high end. So I'm still figuring that out, but we'll get there eventually. The next test we'll do is signal to noise. So go ahead and load that test here. Now the Rohde & Schwarz analyzer makes you use a weighting. If you try to run a signal to noise test without some sort of weighting, either the A weighting or the CCIR, it'll complain and tell you need to use it. So we'll do A weighted, because that's kind of the standard here. Let me turn that off. Generator. Okay. Switch this to unbalanced. Alright. So it's measuring about 86 dB. The spec was 90, but again, I'm not sure how they measured it, what sort of equipment they were using, and my house here with modern LED lighting and other sources of noise probably isn't the best test environment, but I'm pretty happy with that. I mean, that's a pretty good number. It's not far off from the Dynaco Mark IIIs that I measured a couple months ago. You can hear it continuing to take the measurements. The next test is going to be frequency response, and the way this Rohde & Schwarz analyzer does it, or at least one of the ways you can do it, is pretty cool. It uses an FFT to show you your frequency response in real time. I'm not exactly sure how they do that yet. I haven't really looked into it too much. Anyways, I've got it set up. The amps have the gain controls turned all the way down on them, but the signal generator is running, and it'll get us to about 40 watts when I turn it up all the way. But watch what happens when I turn the gain up. So the gain on the left amp is all the way counterclockwise right now, which is labeled 10 on the numbering. It's actually supposed to be from 10 volts counterclockwise to 0.7 volts of sensitivity fully clockwise. And you'll see, and keep in mind the output impedance of the analyzer is very low, but as you start turning it up, the high end rolls off until you peg it all the way fully open. So I'm going to suggest that he keep the volume control fully clockwise and handle the volume from his preamp. So that's the left channel amp, and now if I bring the right channel amp up, we'll see the same type of thing. Same exact roll off on the high end that we're seeing on the one on the left, but you can see that they're nice and flat otherwise from 20 hertz to 20 kilohertz. And this is at a full 40 watts of output power. For this last test, we're going to see how much power they make at clipping. I'm going to give them a 1 kilohertz signal. I've got it set to 400 millivolts right now, which isn't quite full power. So let's turn that on, take a look. So they're making 21 watts at about 0.08% distortion. Let's move that up to 500 millivolts. Alright, 33 watts at about 0.2. And I should see around 40 watts at 550 millivolts or so. So there we are, right around 40 watts at less than 0.5%. And there's no filters on here. There's no high pass, low pass, or weighting filters. And let me actually turn this other residual distortion waveform on if I can find it. There we go. So the bigger waveform is the sine wave from the monitor output on the amp, and the smaller one is the residual distortion waveform. So let's start cranking this up here. Go to 560. So we're at 42 and 44 watts, around 0.5. So 590, we're at 45 and 47. Still not seeing any flat topping on the sine wave. So at 50 watts at 0.5 and $55 watts and still below 0.1%. That's really good. Alright, there we go. So we made 57 and 59. And we can see at 56 is we're around 1%. So I'm really happy with that. That's really good. It's much more than they're rated to make. Alright, one last thing I'll show you before we end the video, and that's the video from the thermal camera showing the temperatures of these amps after they've warmed up and have been running, and what a big difference the capacitor heat shield makes for the capacitor. You can see the capacitor's hanging out at around 70 degrees where the tubes are over 400. That stick resistor's over 400, so I think it's a worthwhile mod for longevity of these amps. And keep in mind there's normally a cover that's snapped on over this, trapping even more heat in there. So anything we can do to keep the capacitor happy is a good thing. Thanks for watching.